Thank you very much for joining another edition of our Liftoff webinar series. My name is Joe Steele. I'm the Vice President of Communications and Legislative Affairs here with Lyft. Today, we are excited to essentially learn about some magic from our friends at Exum Instruments, here to talk about some new technology for rapidly characterizing chemicals and other materials that capability that is now resident in our Lyft headquarters in Corktown, the Corktown neighborhood of Detroit. So we are excited about today. I do have a few housekeeping items to go through. First of all, thank you so much for joining us today. Everyone should be on mute. If you are not, please go ahead and do so. We are recording this session, so it'll be made available to folks afterwards. So if you missed something, want to revisit something, want to share it with your friends and family who were unable to join us today, you'll be able to do so. It'll be posted on our website at lift.technology. If also during the presentation, if you do have a question, please use the Q&A function that is on the Zoom toolbar. Try to avoid using the chat function. Q&A function is much better for handling the Q's and the A's. And we will take care of that afterwards. We're actually trying a new format for the Q&A session for today's webinar as well, which we're excited about. So I do want to take a couple of minutes before we hand off to Jeff and team from Exum. I want to tell you a little bit about Lyft. Lyft is a nonprofit public-private partnership and Department of Defense Manufacturing Innovation Institute. By all that, I mean our mission is driving American manufacturing into the future through technology and talent development. We know that the future of our economy, the future of our national security rests on the advanced manufacturing sector, and we want to make sure that those advancements, both on a technology point of view and a talent point of view, are being led here out of the United States of America. And so that is our mission, to make sure that we are advancing those technology and talent development issues first here. So how do we do that at Lyft? We do that by solving the manufacturing equation. We live at the intersection of material science, manufacturing process, systems engineering, and talent development. Put all those together. We want to make sure that we know what we need to make in the future. So we need to take a look at what we need to make those materials, what we need to make those components out of. How do we then make them to make sure they fit in the system that they're going to be working in at the end of the day, and to make sure that we have the talent that is advanced manufacturing talent that is available to work with these new technologies when they make it to the shop floor. So it sounds like a lot of things, and it is, which is why we have a national ecosystem of members, and Exum is one of our more recent members, so we're thrilled to have them on board. So at Lyft, we tackle everything by the two programs that we run: Leading Innovations for Tomorrow, which is our technology program, and Learning Innovations for Tomorrow, which is our talent program. Touch on both those briefly. The technology program, all of our projects and programs live under one of these four pillars of technology, starting all the way from integrated computational materials engineering, basically looking at materials in the virtual world, understanding what makes them tick, how they will react to a process, and be able to run the process to understand how the materials are going to react, so we can predict them, what's going to happen in the physical world. All the way into advanced alloy and process development, and taking those models, building the materials to make sure they're fit for purpose. And as we're developing new materials, we have to understand how to join them. And then agile and smarter manufacturing, really taking a look at are there new ways, new techniques, new processes we can undergo to make things in the manufacturing world a little more nimble and a little more agile for us. So a little bit more detail on the screen here. If you do have questions about any or all of these, you can reach out to us at Lyft, and we'd be happy to walk you through them. On the talent side of the equation, it is still about innovation, still about new tools, new pathways, new venues, but now we're talking about the ways in which we educate the advanced manufacturing workforce of the future. And that really all begins the Lyft Learning Lab that is in our Detroit facility. It's kind of a pilot plant, if you will, where we bring new curriculum to the table, test it out, make sure that it fits the purpose that we need. We bring teachers to the table, bring students to the table, so they can see what advanced manufacturing looks like in 2023, and then those opportunities are rolled out around the country. And that really takes off with Ignite. Our high school program is a foundational program for high school students around the country, a 3-year program where they get to take a look at advanced manufacturing and hopefully move that direction in terms of making their career choices or future education choices. We also have a couple of programs that we run for our more adult learners in terms of certification for jobs that are available right now today, both LIFT certified programs and Operation Next, which is a program that is designed for separating service members, their families, National Guard and Reserve members in a way to prepare them for their civilian careers once they move out of active duty, or if they're in the Guard and Reserve and want to learn a new skill, upskill. All of those folks can learn CNC machining, welding, industrial technology maintenance, or robotics, earn a nationally portable, industry recognized credential from LIFT, kick off those careers today. So I did mention finally that we are a nonprofit, public-private partnership and membership-based organization. So what do folks get out of becoming a LIFT member? Well, all the things you see on the screen here. We're not here to sell a specific product or service. We are a trusted advisor to give you the best advice we can to help move your technologies into the future. And then you see further on down the list, we're a technology accelerator, technology showcase, which we'll see today, both technology accelerator and showcase from our friends at Exum. We're a connector and a convener, bringing the best and brightest from advanced manufacturing together. So you're a part of that today. Thank you so much for joining. Talent developer, already spoke on that in terms of educating both the advanced manufacturing workforce for today as well as in the future. And finally, we are a government partner. It can be unwieldy to work with the Department of Defense and federal government, particularly for our friends at small companies, even large companies can find it challenging, but we can be a conduit to do so. So that is enough on LIFT. Please reach out to us if you have any questions or comments, but I do want to turn over the program to Jeff Williams, the CEO of Exum Instruments. So Jeff, I'm going to stop sharing my screen if you want to go ahead and share yours, and the program is yours.
Perfect. Can you guys see my screen okay?
Yeah, we can see you.
Yep, perfect. All right. Well, thank you guys so much for jumping in here. Again, my name is Jeff Williams. I'm the CEO and co-founder of Exum Instruments. So my background was in analytical chemistry. I got to pretty much, utilize every acronym you can think of tools out there, from XRF, ICP-MS, and everything in between. And really what I found was that if you needed to take a solid sample, so whether this was a piece of metal, some powder, a ceramic, plastics, anything solid in the world, the best way to get it analyzed was to digest it in a bunch of acid, do a bunch of complex chemistry through it, and send it out to a service lab, more than likely, and run it through liquid techniques. And what I wanted to do was create a technology that you could put anything solid into, access the whole periodic table in one analytical session, and make it as easy to use as an iPhone. So I wanted to ensure that you didn't need 2 PhDs running this instrument. And that's really where the MassBox fits in. We can do anything solid, we can access the whole periodic table, we can quantitate, and we make it as easy to use as an app on your phone. So I'm just going to play a little kind of intro video that maybe some of you have seen on our website if you've checked us out. But essentially, this is an instrument, as you can see behind me, that sits on a desktop. So this could sit in a lab space right outside of your shop floor, that you can be printing parts, cutting parts, or getting new materials in and analyzing them within an hour. So desktop instrument uses a new technology called laser ablation, laser ionization. So what you're going to do is take your sample, this could be a powder, a piece of cut metal, and you're going to load it into our sample holder, which you'll see here in a second. So sample door pulls out, which is right behind me. And we're able to take this material and do bulk characterization or elemental mapping, which we'll see. So we're going to use a quarter for this example. It's going to take a large image of the sample on the screen, And we can now choose to do lines, spots, or rasters. The door then closes and we go under a high vacuum environment. One laser is going to come down and hit the sample and create a neutral particle cloud. And the second laser is going to come in and create our ions. This is what we're actually going to be analyzing through what's called time of flight mass spectrometry. We basically kick the ions really hard and they fly as a function of mass. So hydrogen goes very fast, uranium goes very slow, and we end up with a time series data. So this can be anything solid, ceramics, metals, batteries, anything you can think of. As long as it's flat, you're going to get answers in a matter of minutes, not weeks sending it out to a supplier. So for chemical mapping, let's say we did a two-dimensional raster here, we can actually choose an element to look at, and we'll actually get a chemical map of what that sample looked like. So was it homogeneous? Was it heterogeneous? What we're running today right behind me was a weld on a piece of nickel onto an iron substrate. We want to look at the boundary. How did the iron diffuse in there? We can look at all of these sorts of questions all within the same machine. And when we're talking about access to the periodic table, I know a lot of people on this call today, they care about carbon and oxygen and nitrogen, and they care about tungsten and molybdenum and niobium. And doing those lights to heavies can be very difficult with other techniques. Sometimes you can get the light elements, but you can't get the heavy elements with the tool. So generally you need 3 different machines to get your full answer. But as you can see with this periodic table on the top here, any element that's colored is an element we can analyze. We can analyze these to very low detection limits. We're talking hundreds of parts per billion. So that's easily covering all industry needs. And importantly, you're seeing we're getting lithium, we're getting boron, we're getting carbon, we're getting everything in the same analytical session. Don't need to do another sample preparation, throw it through one machine, quantitate it, through another machine to quantitate it, all done at the same time. And really what this comes down to is, let's say you're a additive powder provider and you have some new titanium, and we know titanium loves oxygen, and we want to make sure that it has the right amount of iron in it. With one standard, a single point calibration curve, and an unknown powder, let's say this is something that you just printed with and you want to do a quality check on this powder, or it's a solid part after you make it. You want to check the oxygen level before, you want to check the oxygen level after. Carbon, aluminum, iron, chromium, vanadium, even hydrogen in here. We did all these elements simultaneously. The black is the certified value. So this is the value that came with this specific standard. And the gray was what was measured with an external lab for the same powder set. And Exum was, within 8% for all quantified elements with an internal precision of 6%. And for a lot of elements, we were actually better than the external lab, kind of validating that, hey, we do get all the light elements and the heavy elements quantitatable within a few matters of analysis here. Anybody can run. We just did a training this morning, and within an hour, Nick was already running his own sample. So next kind of use case I want you guys to be thinking about is chemical mapping. And so this is a project that we did with NIST when there was a lack of fusion within a pore space, and they want to analyze what elements are in this pore. And we need to look at it on the parts per million level. It's something that our SEM isn't going to tell us. It's something that our laser confocal isn't going to tell us. We need this kind of gap between an SEM and doing full digestion. That's where we sit here. So on the left, the pore you can see in our micro image that you're able to zoom in and look at. It's about a 750 micron by 750 micron viewing area. We then put a raster analysis over it. It kind of scans like an old CRT TV, and we're able to then create chemical maps. So you can look at all of these elements. So this was an aluminum base, so you can see aluminum is very bright in the first map, and you can see that lack of aluminum in that pore space. But you can see it's filled with carbon, it's filled with iron. There's something going on with the titanium and the oxygen levels as well. And so they were actually able to back out, oh, that was probably an impurity piece of powder that was there that wasn't fusing during this additive process. So you can use this for all sorts of things. Welds, like we're doing in the back end. You can average compositions like we're talking about, or boundary space, or coatings as well as another thing. Because this is an ablative technique, we're moving about 100 nanometers per layer. You can keep stripping down. You can go through your chromium coating on top, seeing what the interface looks like between your sub and going right down into your substrate and doing your chemistry all the way in between in 3 dimensions as well. So tons of applications for that as well. This is just a short video kind of showing what it's like, what we just did behind me when looking at the samples and what it's like to set up a raster. So we took that image you saw. We can choose a line scan. We can choose spots. You can change that spot size between 1 micron to 150 microns. You can set up a raster, do the same thing, make it bigger, make it smaller. Maybe you don't have a lot of time on your hands. You want to do a fast one, or maybe you want to set up overnight and do the whole quarter here. Fully adjustable. So you can kind of see, how big it's going to be. It's also going to show you on the sample in the micro view exactly where it's going to analyze. So you can be sure like, oh, I'm analyzing exactly in that pore space that I really care about. So that macro image is correlated to the micro image, and those spots are perfectly overlaid. So you know exactly where you're getting your analysis from. During this whole process, all of the vacuum, all of that sort of thing is a fully automated procedure. So you don't need to think about it in the way you might have had to on other techniques. So it's that easy. This screen comes up, spots, you press next. And let's say we had done a raster map that we wanted to make an image out of. It's as simple as going to this data screen, click generate heat map, choose the element on the periodic table you want to put a heat map for. So we want to map copper here. And we're going to see that, underneath that copper was actually a bunch of zinc. And so there's blue over the E where we sanded that down in this penny, because pennies are actually just a copper top with a zinc underneath, and we can see that in this chemical image here. So, and each one of those pixels to think about is a single laser spot. And you can see what's true for copper being low there, zinc was high. So the inverse, because we get every pixel, we get a full mass spectrum. So we're able to choose whatever we want and look at every single element we're interested for every raster. So you get all the data at any point in time. And that's a really important point that I want to stress there is if you're a company that's sending out for samples to be done, you kind of have to know ahead of time what you're looking for, right? You need to know, hey, measure my carbon, measure my oxygen, measure my iron and nickel. But let's say some other time, you know what? My molybdenum was an issue. We get all that data. You can go back and reprocess that data and understand what that molybdenum was doing. You don't need to rerun that sample. All of the information in time of flight is stored for you. You don't have to know ahead of time what you're looking for. And that can be a really critical thing. So I don't like to talk at people too long. I want to, leave a lot of time for Q&A here. So I'm going to go ahead and stop sharing my screen and turn it back over, and we can get to some questions.
Awesome, thank you. And as you can see, as we as an institute are focused on materials and manufacturing process, I mean, you can understand how critical this is going to be to the work that we are doing going forward. And speaking of the work that we are doing going forward, I'm going to introduce and turn over the program and the Q&A portion of our program over to John Keogh, Lift Director of Engineering, who's, if you've been to our Lift High Bay, that is his playground. I'm sure if you have not been to the High Bay, John would be happy to show you around and walk you through all the different toys that he has at his disposal, including the newest one from Exum. So John, take it away.
Thank you. The newest and the most exciting. So again, thanks everybody for joining us. I'm John Keogh. So I want to set the stage really quick as to why we're here. So as Joe mentioned in the introduction, we focus on materials, processes, and manufacturing, and we really leverage our efforts against the development of solutions against extreme environment applications, at least in the technology space. What that means is that we typically think about hypersonics, we think about armor, artillery, all of that orbits around new advanced materials. And we have a set of massive initiatives that I don't want to speak too much to, but a set of massive initiatives that involve the development of custom materials in meaningful volumes internal to lift in Corktown in that facility right off to my side, really behind the viewers here. What that means is for us to be able to develop materials, you have to be able to not only simulate them in the virtual space to try and accelerate and offset the empirical make and break effort that normally incurred, but then you have to manufacture those materials and you have to test those materials to understand not only the chemical composition, but their properties and performance and all that. And that all forms kind of a holistic loop of design, manufacture, and test. And as we're moving forward in these initiatives and as we're planning them out, it became clear to us, so right now we're sitting in a world-class MET lab. The only thing that we were missing was something like a mass spectrometer or a mass box. We have SCM with EDS and all the other stuff for metallographic and microstructural analysis and so on and so forth. But the question came up really, what do we want to do about chemical analysis? Do we want to look at an ICP system, ICP OES or ICP MS? Or do we want to look at something else, mass spectrometry in the LALI system, for instance, that you see here behind Jeff? And there are significant drawbacks in the existing technology, all of which are addressed when you're talking about solid state sample analysis with this instrument right here. So for a little bit of background, Jeff and I are kindred spirits. Okay, I'm also an analytical chemist by training as well. I also have background in mass spec, although not nearly as much as Jeff. But once I learned about their platform and what they're doing, it was obvious that this is the right choice and that we need to develop a really good sound partnership with the Exum team, with Jeff and all the rest of the team for many different reasons. And so for that purpose, we recognize the value of the technology. It really is truly transformational. And so we hopped on the line and started building a relationship. And next thing you know, now just recently, the baby came home from the hospital, if you will. And we're running an analysis right now on, as Jeff mentioned, a nickel weld on a 4140 steel substrate. So with that, I mean, what we're really doing is moving into kind of just a Q&A session. So this is kind of just an open environment. If anybody has any questions, please feel free to add them to the chat. I think that it would probably be useful to start out and maybe set the stage in terms of, all right, so we're using a lot of acronyms right now. We're using ICP, right? We're using MS, we're using OES or whatever else. So Jeff, maybe if you could take a minute and just lay out the landscape of maybe what the competing technologies are for chemical analysis of these types of samples, and their drawbacks, lead times, things like that. What mass spectrometry is really as well for maybe the uninitiated.
Sure.
And then there's gosh, I have 1,000 questions, but go ahead. Yeah.
I'll start with start at basics. What is mass spectrometry? What are we fundamentally doing here? So mass spectrometry is making a spectrum of mass, right? So all of the elements weigh something different, right? So how many protons and neutrons do they have to find their mass? So hydrogen is the lightest element, it has a proton in it, and uranium being the heaviest element has a lot of protons in it. And what we want to do is, how do we separate these things out? How do we see a hydrogen detection different than a uranium detection? So mass spectrometry is really all about separating mass. So there's a lot of different ways to do that. Well, actually, before I get to how we do it, the fundamental way we can communicate with one of these atoms is we need to make them into an ion, right? We need to strip off an electron, or we need to add an electron. And the reason we need to do that is once it has a charge to it, it becomes able to be manipulated by an electric field or a magnetic field or both, right? It can be pushed, it can be pulled, it can be kicked, or it can be steered. And so mass spectrometry takes advantage of this in a lot of different clever ways. But fundamentally, what we're doing is we're taking that atom, we're either putting it through an electric field or a magnetic field, and we're making hydrogen do something different than what uranium is going to do. And as long as we can detect where that happens, we're going to get a different spectrum, so mass spectrometry. Specifically with Lolly behind me, use what's called time of flight. So you saw that in the video, where we basically kick them really hard voltage. And it's like kicking a soccer ball or a bowling ball. If you kick them with the same amount of force, a soccer ball is going to go very fast. That's your hydrogen. Your bowling ball is going to go very slow and hurt a lot more. But if we look at it in a time spectrum, if we're just following along time, it's going to be hydrogen, carbon, iron, and it's going to come in that sequence. And then we can convert time to mass and then automatically integrate those peaks. So the second part of your question was like, what does the landscape look like right now if I was like, you know what, I really need to analyze this cup. How am I going to do it, right? So there's really, I would say, 3 key players. Right now we have XRF, which is really great for a lot of applications.
And that stands for?
XRF is X-ray fluorescence. So you're going to hit something with some X-rays, you're going to look what bounces back. So it's not a mass spectrum. We're actually looking at a light spectrum, essentially, and have a limitation of what part of the periodic table we can look at, and also the detection limit. How low can we see? And also we have a limit of matrix matching as well. So what I mean by that is whenever you hear matrix matchings is, are we analyzing a 316L and are we standardizing with a 316L, right? So sample and standard have to be very, very closely matched in that technique. But there's a lot of applications, this is great, where so actually we'll just leave XRF as there. So X-rays hit, we look at the spectrum, we need tight sample standard matching, probably looking at things more in the high thousands of parts per million to weight percent level. And we're not going to get our carbon, our nitrogen, our oxygen, our boron, our lithium, any of those light elements. Oh, perfect. Alan's actually pulling up a slide right here. We also have LAICPMS. So that's a lot of letters in there. But so this is laser ablation, inductively coupled plasma mass spectrometry. This is a great technique as well. Has very, very good low detection limits, but it has a lot of limitations when it comes to ease of use. You need a clean lab for this. You need, analytical chemists on staff for this. You need 2 different instruments from 2 different companies. You have a tube kind of connecting them between, and quantitation can be quite cumbersome. And also you have high consumable rates as well as a difficulty with light elements. But what LAICPMS is doing is you're ablating some material, you're carrying it with an argon gas flow to a plasma torch. That plasma is going to be your ionization source. And then we're going to another type of mass spectrometer to separate out those masses. And in this case as well, you need to know ahead of time what you want to look at, because these types of mass filters don't get everything no matter what. You have to tell it, hey, look at carbon, look at magnesium, look at iron. And if you don't tell it to look at something, that data is gone forever. The other one I'll quickly touch on is LIBS. LIBS is a great qualitative technique, especially in the recycling industry. Is this a stainless steel? Is this an aluminum? You'll find a lot of handheld systems to do that, but it has a lot of quantitative limitations as well as detection limitations. But basically, LIBS hits a sample with a laser, creates an instantaneous plasma, looks at the light from that plasma, and does the analysis. I know that's a lot to take in, but that's basically the market overview and where we kind of sit. We get the whole periodic table, we're easy to use, no consumables, and quantitative.
Perfect. That's great. So, so quantitation historically then with mass spec can be a bit of a challenge.
Yeah.
But from what I understand, the way that you have architected your sample introduction, extraction, ionization stage, and all that for ablation, the laser ablation, laser ionization allows you to be largely matrix immune, right? And you touched on matrix effects a moment ago.
Yeah.
And maybe you could just expand a little bit about on that. How does a matrix effect arise? Like, say, do the elements when they're adjacent to each other, say an XRF, for instance, preferentially emit? Or do they preferentially ionize when they're coming from the bulk in a mass spectrum? And how does the Lolly platform get beyond that and end up having a stoichiometrically representative cloud of neutrals that you can then blast with a laser and make a good plasma?
Yeah, I'll take LIBS is probably the closest analog here. So we'll take like libs and like the challenges there.
Yep.
So when we have libs, we have a laser that's ablating a sample and creating a plasma.
Mhm.
That plasma is basically an energy limited environment, right? So it's only going to be able to have so much energy to ionize everything that's there. So if you have a little bit more sodium, which loves to ionize, or a little bit more potassium, you're going to quickly end up in this multivariate space of ionization and therefore quantitation. And that's why it becomes very, very difficult. Now, what we've done is we've optimized the opposite of libs on the ablation side, and we want to create the most neutral as possible with the least amount of plasma, actually get rid of the plasma. And we use a type of ablation called ultra fast. So it's a picosecond laser, very, very fast. And it creates a more stoichiometrically representative. So stoichiometric meaning it is representative, the proportions are correct in the neutrals as they are in the solid, right? So it's more proportional in the neutral cloud. We then hit it with this secondary laser to ionize it. And that creates a saturation of ionization. So we don't have a limited system here. We have so much power in that ionization that we can flood it basically. And we make sure we're ionizing anything that laser is touching. And this is what helps us to what John was just alluding to with the more matrix insensitivity or a larger dynamic range that we can get to between sample types is because we have this kind of saturation of ionization and therefore ease of quantitation with standardization. That was a lot of words. And we can go into more details with that in the question and answers, but it basically allows us to make calibration curves more linearly across a different range of chemical compositions.
Perfect. Thank you.
Yeah.
So we have some questions coming in from the audience here. So let's see here. We'll just go straight down the list. So have you tried to apply the technique to determine surface cleanliness?
Yes, actually, that is something that we routinely do is we do what's called a cleaning run because, you know, somebody's touched the sample, you got all these oils on it, or let's say in part of your process, it sat out in oxygen for too long as well, if it's a titanium, or maybe there's some machining oil. You'll see that in the mass spectrum in the first pass. You'll basically see all of these peaks that are basically organics, or maybe they're a coating that's on it. And so what we do for quantitation runs is we'll run that first pass, we'll look at it and we'll say, okay, that looks pretty dirty. Let's run it again, same area. And we keep going down until we get to the clean base metal. So not only can you get information of what is contaminating my sample, but we can also get through that contamination to what you care about on the substrate.
Perfect. So are you saying that all detectors read out at once, or does the user have to select one detector at a time? Now, I'm not sure if they're asking about the individual pixels in your MCP detector, or if they're talking. So just expand on how we detect and how we read out also, perhaps.
So the detector is a single detector. It has an array of like tubes in it, but they all read to one voltage essentially. And so the masses are actually separated out in time. So the hydrogen will hit the detector, it will get a signal, it'll come back down to background, and then the carbon comes. It will get a signal, it will come back down to background. So the user has to do nothing. We will automatically detect all of the elements that are in there. We'll find those peaks like John just saw like an hour ago, and actually what we're doing right now. We'll automatically find those peaks for you, we'll calibrate them, and we'll actually populate on the periodic table so you don't have to know like, oh, is there iron in here? We'll tell you, hey, there is iron, there is carbon.
That's perfect. Yeah, the interface, just a quick comment, the interface is absolutely amazing. I mean, you definitely achieved, when you say you want to make it as easy to use as an iPhone. I've slaved over mass spectrometers in the past, and I've slaved over data analysis and databases and interpretation and all that. This is amazing. I mean, I'm absolutely I'm floored. I'm giddy about it. Those of you that know me that have spoken to me about this know that I can't shut up about this platform. It's just amazing. So you guys have
Thank you very much.
Really, really incredible
The software
work.
team will be very excited.
Good, yeah.
Because I've been very hard on that.
Oh, good. Okay, well, keep it up. All right, so then if you wish to get a bulk analysis, does a sample need to be homogeneous, or do you average results from several sampling spots, or is it a la carte?
Yeah, exactly. So what like Ellen's showing on the screen right here, that upper mass spectrum that's showing up, that's an average of everything that we just analyzed, right? So that's taking that entire raster run that was just done and averaging it up into a single mass spectrum. But you can also look at this in a time series view as well. So you're seeing on the bottom, they're looking, did that signal vary through time? Was it very noisy, maybe like what it's showing here? And that might tell you that the sample is very heterogeneous. And so if you have a heterogeneous sample and you still want to get a bulk average, you just run a larger area. You try to get as much statistically, representative amount of that sample analyzed, and you can then get a bulk average as long as you have, good matching for it. And you can use that heterogeneity to your advantage too, to say like how much heterogeneity is an issue, and the mass spectrometer can tell you basically a number, like it's heterogeneous to this level. And that's kind of a quality control check for you too. If all of a sudden you hit a certain value and you're like, you know what, there was way too much titanium I mixed in there.
Yeah,
that was a problem. So you can use it as a screening tool as well.
That's perfect. And you mentioned that your ablation spot size you can change anywhere from 1 micron up to 150 microns in diameter. Really, it's a square, right? But
it's a square.
But I mean, with that said, then if you architect your experiment right, you could even go down to doing single particle analysis. Say if you had a sample of powder and you wanted to look from particle to particle on, I don't know, 20 to 40 micron, diameter particles, then you could go from one particle to another, and actually you could do rasters on each individual one.
Exactly.
And so we're actually getting to some of the nuance in terms of sampling bias and how you select the sample, what constitutes an average, and where you really care about, and what is your sample, but yeah, it's just amazingly versatile.
Yeah, exactly. And to that point, let's say you did a raster map and you saw you had this big old spot like we saw in those core samples for the NIST earlier. And let's say, or like what Ellen just brought up here on the screen, right? This is actually a mixture in here. And we can actually see that it's not perfectly mixed, right? If we look at where the iron is maybe a darker blue, that's actually a lot of titanium and niobium. So in this mixing, maybe that's an acceptable amount of nickel and iron mixing with the titanium and niobium. Maybe it's not. Right? But also, if you're interested in, let's say you get a really, really hot spot in there, you can go back exactly where you analyzed on that map, put a spot, and just dwell into that single particle. Yeah.
Drill down. Yep. That's awesome. All right, so we answered the bulk analysis one. There's two that actually kind of overlap with each other. So we're ablating material, right? And we keep doing that, and eventually you get some fugitive material in the chamber, right? So what sort of cleaning and maintenance is needed periodically in the chamber? Is that ablative condensation? And kind of, what sort of system maintenance overall is required, and what sort of interval as well?
Yeah, that's a really good question. So yeah, we the ablation, we're actually not melting because we're doing ultra fast cold ablation. So we're not like putting a whole pool of melt everywhere, but we are releasing neutrals, right? By definition here. And those neutrals will basically start thin film coating the glasses that the lasers come through. And so we have a system built into there that's basically a sacrificial window. And so every so often you'll move it and you go to a fresh piece of glass. And so you have more than a year's worth of glass in there. So basically, 96 different locations on these glasses. And so if you're moving it once a week, it's going to last you almost 2 years.
Is that a manual move?
Nope. There's in the software, you press
go.
advance, it just goes automatically for you. You have 100% power given back to you.
Again, so incredibly user friendly.
Yep. So you don't even have to think about it. You just press forward, gives you new power. So that happens on a 1 to 2 year time scale. We'll come in and put a fresh piece of glass in for you. And we have a water filter that we change out about every year as well. Perfect. That's the only routine maintenance that happens on the instrument.
And then just the extraction stage, you just swap out once.
Yeah, good point. So actually, I'll grab it right here. So this little extraction stage.
There you go. And Ellen's showing it too.
And perfect. There we go. So this little extraction stage, we basically give you 2 of these, and you'll get a little bit of powder where Ellen's putting the mouse on there. And you basically want to just take a Q-tip with some IPA, wipe it down, get the powder off, and you can put a fresh one back in. But again, we give you 2, so you take one out, put a new one in, you're up and running instantaneously. Perfect. You can even throw this in an ultrasonic cleaner if you wanted to, and then you're good to go.
That's perfect. Yeah, I love how user friendly that is. In the past with electrospray instruments and things like that, taking that whole extraction stage apart and cleaning it, it's an entire day effort often, and you have to be incredibly careful, and everything's very sensitive. And, oh, it's amazing. Yeah, it's just amazing. You know, it just boggles my mind. You know, so in school, we both probably had to make our own instruments, and you know, often you can breadboard an instrument that is as good or better as something that's commercially available, at least as far as linear dynamic range or detection limits and things like that. And when you see that that's possible, it's bothersome the how difficult it is to access chemical instrumentation, how difficult it is to operate it. You know, and you guys really have democratized that. So, all right, so we talked about condensation and cleaning. This is a perfect question here. So we were talking about ceramics and organics and things like that. And you know, again, just to reiterate, at Lyft we're working with materials, broadly speaking, for extreme environment applications. That could be metals, that could be ceramics, that could be composites, ceramic matrix composites, polymers, for instance, as well. So it's my understanding that you know, we can quantify. We're very comfortable qualifying and quantifying in the metal space, and in the ceramic space we're talking about that as well. The system's perfectly capable of ceramics as well. But let's touch on organics and polymers and things like that, and what you can do there.
Yeah, absolutely. So yeah, like you said, for ceramic space, absolutely we can hit ceramics. We've done some as well, but we haven't, you know, fully flushed out applications on there. But we're really excited to work with customers that they have specific ceramics. We'll set you up and you'll be up and running on it. Yeah, on the polymer space, let's say, you know, right now if you wanted to do elemental analysis in your polymers, you can do that as well. How much iron is in there? How much vanadium or whatever else you might be trying to throw into their carbon? Absolutely can do that. Now, something that is built into our machine that we will be basically unlocking as a feature is we have the ability to switch between that UV beam that we do ablation with to an infrared beam. And that will basically allow us to do organic analysis as well. And you can do fragmentation, and you can actually look at the fingerprint of your polymer list. And so you can kind of get a rough estimate of what molecules are in there. Is there a difference batch to batch? And so that's something that's already baked into this instrument behind us. And it's just a software update that Lyft will get one day that's like, hey, we want to do polymers now. And here you go.
Go ahead and touch the screen.
Yeah.
So that's fantastic. And so then for the polymers then, or just organic molecules in general, with that infrared source, then we can use that for interrogating the matrix of, say, carbon composites, right? And we can look at the gradations and you know, maybe have some unsintered or you know, unceramicized pre-ceramic polymers or things like that, and you can begin to look at not only the elemental distribution from a quantitative perspective, but you can also begin to qualify, at least, based on, you know, some knowledgeable use of the system, qualitatively, what molecular species are there as well, right?
Yeah, exactly.
So yeah, so it's that, and that's just I mean, it's amazing, the capabilities there. So all right, so we addressed that. You know, so there's some comment about infrared spectroscopy comparisons. You know, this is really giving you spatial data as opposed to typical IR, where you're taking a sample, you put it on a, you know, either on a ATIR system or something like that, and you just basically are getting an average over an illumination.
Right.
This, again, you're getting spatially resolved data. So sample size, let's talk sample size, polishing, sample prep, requirements, things like that, the sample stage. Alan, you're on it. This is great.
Yeah, perfect. So basically all we need is something flat and solid, or at least pseudo-solid, right? So this can be a 3D printed part. It could be a powder pressed into a puck. It can be something like a coupon that you use for testing on your, let's say, mechanical test. So you went over and you broke it, and you want to say, what's the chemical composition of that test I just did? Take the same coupon, throw it in there. Just to be solid and flat, and less than 1 inch in height. Our sample stage, as you can see here, is about 3 inches by 3 inches. So anything that you can fit on this stage, you can analyze. And then also we have basically fully customizable stages as well. So basically this is a top that just pops on and off. So if you want to do microscope slides for something, let's say you have thick sections or thin films that you want to analyze as well, we can hold those down. Or like what we're doing right now with this weld piece, we're just putting some carbon tape on it, sticking it to the stage and shoving it in.
That's perfect. That's great. So we talked about size, sample size, polishing requirements. How long does it take to test a sample?
So it depends on how big of an analysis you want to do. So for example, we just did some pretty large maps across this big boundary of about, I think it was like 10 millimeters by 5 millimeters across this weld boundary from nickel to substrate. And that took about 20 minutes to do it twice. So within the time, that we've done this webinar, we have all the data we need to look at how was that melt pool doing.
And then what about pump down time? So you have the chamber open, you put your samples in, you press close, and then how long until we're ready to go? All the lights are green and then the laser starts firing. Yeah,
so about 10 minutes till you're doing your first analysis. So, and after that 10 minutes, what we'll generally do is we'll do our first cleaning run. Somebody asked about like contaminations on the surface. We'll do a first pass. We'll say, hey, what's the surface looking like? Maybe we want to clean it off. And then for the quantitative runs, we wait about another 5 to 10 minutes or so, or while it's being analyzed, we go back, put our quantitative runs in, and we're up and running. So
that's awesome. Yeah, if I remember right, when I came and visited you guys in Denver, it took 6 minutes.
Well, there you go.
Well, down, so.
Listen, I like to beat expectations.
I'm with you. So then one of the things that I really like is really the spatial resolved information. And, that has value from so many different directions and for so many different reasons. Can you compare and contrast the spatial resolution that you get with SEM and the pros and cons there? Because SEM, depending on the instrumentation you have coupled to it, you can get some pseudo quantitative up to quantitative chemical information, but that comes at a cost. And again, there's all kinds of, so maybe just give some flavor there and compare
absolutely.
And contrast, but I think they're complementary.
Yeah, and so so for anybody not familiar with SEM as well, SEM is basically taking an electron beam and it's scanning, right? And electron beams are very, very small. And so if you're looking at something like, let's say this pore space that Ellen has on here, you're going to be looking at it basically inside that pore. You're not going to be able to really like see this whole 750 micron by 750 micron spot and get the chemical map within a couple of minutes like we just looked at. Like this probably took 2 minutes to analyze, but when you're scanning with an electron beam and you're trying to do elemental work, it's going to take a lot longer, and you can't see the whole sample at the same time because of how small that electron beam is. So SEMs are great tools for sure for specific applications, especially when you're looking on the nano to 1 micron scale, right? Like it's all a matter of scale. And this is a great example of why we just are selling tools into the battery industry now, right? Batteries need to be in a vacuum environment because lithium loves oxygen and loves to blow up, as we've all heard in the news lately. But when you're trying to analyze it, trying to find that place where you want to analyze an SEM can be difficult. Kind of just hoping that you randomly stumble across this one spot. Whereas with our tool, we can see this whole 3-inch by 3-inch area, and we can map chemically very fast and get down to parts per million level, parts per billion level detection limits, the whole periodic range, and quantitative. Whereas in SEM, maybe you're looking at a very small area, and I don't know how many hours I spent in the basement on SEMs, but trying to hope to stumble across the spot that you're looking for, it's going to show you where your quality control issue is. And so in the battery space, we can map a whole battery, and we can look for these like little dendritic growths within the battery substrate itself. And we can look at every element simultaneously.
That's amazing. And have you guys been able to resolve microstructural, differentiation, at least on large microstructures, perhaps?
Yeah, if there's a chemical boundary, you'll see it. Just like what you're seeing here.
Down to 1 micron and
100%. So so like especially like quantitative work, we like to stay at the 10 micron range for sure, because you'll get enough signal there. But actually we have like battery images we did at 11 microns.
There you go.
And you can see really sharp chemical boundaries there, as long as there's a gradient. Actually, here it is right here.
Look at that.
So every spot, this is a LLZO substrate for a battery. You're looking at lithium up to lanthanum here. And you can see very sharp chemical boundaries, even at 11 micron spots.
That's awesome. And while we're on the topic of chemistry as well, so you showed earlier the periodic table detection limits for a lot of elements, and you and I were talking earlier about technetium, for instance.
Yeah.
The reality is, if you had a sample of technetium,
Sure.
you could detect it.
Yep.
Right? It's just that you don't have a particle
Yeah,
accelerator.
very expensive sample.
That's correct. Yeah, but I mean, a lot of those elements, they're white because they're not available.
Yeah.
Right.
Exactly.
So it's not a limitation of the system.
And we don't do noble gases.
Right.
That's our
yes.
limitation.
Yep.
So
Exactly.
that's what I like to say is like we do every element but noble gases or gases you need to make in a particle accelerator.
Yes. Exactly.
Or,
Yes.
elements. Yeah.
Yep. Exactly. Well, I mean, this is for solid state samples, right?
Yep.
So
Exactly.
now, okay, with that question actually, so you can make compounds with say xenon and radon actually, right? You can make those compounds and you can get solid, at least for the radon ones, I think you can get actually solid samples. Hypothetically, if I had a molecular compound of one of these very heavy noble gases, do you think that
if it's in high enough, if it's like a pure, let's say like dimer of krypton and something else, right? And you have like a lot of it.
Yep.
You will see it in the mass spectrum for
Okay.
sure. Our ionization efficiency is going to be very low.
Sure.
Because it's basically built on the first ionization potential for noble gases is so high. That's why they don't like to play with anything, right? So we have to take a lot of photons to beat them up to rip off an electron.
Yep.
So you'll see it. It'll just be like much lower detection efficiency.
Yeah. And actually, we did see hydrogen earlier as well. You just don't quantify it, right?
We don't quantitate it, and it is there for sure. It's application development that we're doing. It's just not something that I like to over deliver.
I agree. Yeah, under promise and over deliver. Absolutely. So then, I mean, I think by now it's clear. You don't need a PhD to operate this instrument. You need a cursory knowledge of the periodic table, but really the instrument does a lot of the work for you. It tells you what's in the sample. Yeah. It's just a matter of learning the interface, learning how to calibrate it and operate it.
Yeah.
So that right there is a map over, say, running an ICP instrument. Typically, an ICP, you have it in a dedicated, service bureau. Or something like that. They have an analytical chemist on staff. They do the digestion. You have to tell them what elements you're interested in typically. Yep. And so in this case here, you literally you set it and you go. And
just like this morning, right?
Yeah,
like
just like this morning.
Nick came in, had never touched the machine, and then within like 30 minutes, he ran his own sample.
Yeah, and you're getting full periodic table analysis. Yep. So actually when a quick testimonial, I mean, one more, right? When I came out to visit you guys, we brought some aluminum F357 powder for analysis. And the spec didn't show that there was any boron in there. As a matter of fact, the spec showed that there shouldn't be any boron in there.
But there was.
And if we hadn't, there was, and when we sent out for ICP analysis, we didn't ask for it, right?
Exactly. And that's key.
And so that's one of the real amazing things is that you get the whole periodic table. Every single shot is a mass spec from the entire periodic table. So I mean, with that, I think I've iterated and shown why we want to use the mass box and why this technology and this relationship is so critical to our initiatives. Yeah. We're endlessly grateful for our relationship and for the work that you guys have done. I mean, it hits me here right in the heart. It's amazing.
I appreciate that.
So, thank you for the visit coming out here. I'm going to hand it over to Joe Steele to send us on our way. So,
Yeah, thank you very much, guys. Great conversation, and John hit it on the head. I mean, everyone listening can imagine why this piece of equipment is so critical to not only what we do as an institute, but what the rest of the ecosystem around the country can do now, and to advancing these materials and technologies forward. And John was not kidding when he said he was very excited, like a kid in a candy store, like talking about this piece of machinery on its way coming was just giddy. So glad to see it come to fruition. So want to thank Exum, first of all, for your membership, your innovations, and your partnership here with Lyft. So Jeff, thank you very much. Ellen, behind the scenes on the ones and twos, thank you very much for keeping up with the conversation. Awesome. John Keogh, our Director of Engineering, thank you very much for taking over the duties of the conversation and Q&A. It's like I had the day off today. So I appreciate that. And then thank you very much to the rest of the Lyft team in the back. Addie Stone Richards, the director of membership engagement, for helping put this together. Philippe Pereira, our events coordinator, for keeping everything going on the ground there as well. A new format, I think, worked out well, and yeah, great conversation. If you guys do have questions or comments afterwards, just reach out to us directly at Lyft. We can get you in contact with the folks over at Exum if there's a question you forgot to ask or didn't get a chance to, or something that hits you later. Please go ahead and do so.
Or if you want to buy a mask box.
Or if you want to buy a mask box, or you want to buy one, reach out. We'll certainly get you in contact with the right people. Want to come by Lyft and check it out in our showcase and sandbox? We'd be happy to do that as well. So thank you very much, everyone, for joining us today. Stay tuned for our next series of webinars coming up in March. In the meantime, I want to thank Jeff and team once again for coming not only to Lyft to do this live, but again, thanks for the partnership, and we're looking forward to see what we can do with this machine going forward.
Awesome. Thank you, guys.
All right. Thank you.
Thanks,
Everyone have a great day.
Bye.
Bye.